Look up at the night sky for just a moment, really look. Those pinpricks of light aren't just stars, they're ancient messengers carrying stories from billions of years ago. Some of them began their journey toward us before mountains rose on Earth, before the first creatures crawled onto land, even before our planet had fully formed. That's the breathtaking truth hidden in plain sight every time we gaze upward. The universe isn't just vast in space, but in time, and right now, we're living through a revolution in how we understand that cosmic tapestry. Modern science is peeling back layers of reality we once thought were forever beyond our reach, revealing secrets that rewrite what we thought we knew about existence itself. Think about this: the light from the farthest galaxy we've observed traveled over 13 billion years to reach us. That means we're not just looking across space, we're staring back into the universe's infancy. And with breakthroughs like the James Webb Space Telescope capturing images of galaxies older than we ever imagined, or physicists unraveling the bizarre behavior of black holes where time itself seems to warp, it's clear we're standing at the edge of a new frontier. These discoveries aren't just for scientists in labs, they're reshaping what it means to be human in a universe so much stranger and more magnificent than our ancestors ever dreamed. This journey we're about to take together isn't just about facts and figures, it's about perspective. When you grasp that the atoms in your body were forged in the hearts of long-dead stars, or that the empty space around us might be seething with invisible dark matter, the world feels different. Suddenly, the universe isn't just out there, it's in you, around you, woven into the fabric of your everyday life. So let's dive into the mysteries that defy intuition, from the mind-bending nature of time near a black hole to the eerie pull of dark energy accelerating the cosmos apart. By the end, you won't just see the night sky differently, you'll feel it. Long before telescopes or space probes, humanity's first astronomers stood beneath open skies and saw more than random specks of light. They saw patterns, stories, even gods moving through the heavens. Ancient Babylonians etched star positions on clay tablets over 3,000 years ago, while Polynesian navigators memorized celestial maps to guide voyages across the Pacific. These weren't just practical tools, they were the first attempts to make sense of a universe that seemed both beautiful and mystifying. Fast forward to Renaissance Europe, where Galileo's crude telescope revealed moons orbiting Jupiter, proof that not everything revolved around Earth. That single observation shattered a world you held for centuries, proving the cosmos played by rules we could discover through observation and math. What's fascinating isn't just how far we've come, but why we kept pushing forward despite limited tools. Johannes Kepler spent years laboring over Tycho Brahe's handwritten star charts, manually calculating planetary motions until he cracked the code of elliptical orbits. Imagine doing that without computers or even a reliable calculator. Each generation hit the edge of what their technology could reveal, only to invent new ways to peer deeper. The leap from Galileo's handheld lens to the Hubble Space Telescope mirrors our own evolution, from squinting at faint stars to capturing the birth of galaxies. Now, with instruments like the James Webb Space Telescope, we're not just seeing farther, we're seeing differently. Its infrared eyes detect heat signatures from the universe's first galaxies, showing us structures so old their light has been stretched into invisible wavelengths by the expansion of space itself. This isn't incremental progress, it's like switching from a candle to a spotlight in a darkened library, suddenly revealing shelves of books we never knew existed. Yet every answer breeds new questions. Why do galaxies form so quickly after the Big Bang? What strange physics governs the earliest stars, the cycle continues, just as it did for those ancient sky watchers tracing constellations in the dirt. The real thread connecting Babylonian stargazers to modern astrophysicists isn't just curiosity, it's courage. Facing the unknown requires humility to admit how much we don't understand, paired with the audacity to keep searching. When a 17th century scholar like Isaac Newton wrote about standing on the shoulders of giants, he wasn't just being poetic. He recognized that each discovery builds on centuries of patient observation, failed theories, and relentless wonder. Today, that legacy hums in supercomputers modeling black hole collisions and radio telescopes listening for whispers from exoplanets. The tools change, but the human drive to unravel the cosmos remains our most constant star. Einstein once wrote that the most incomprehensible thing about the universe is that it's comprehensible at all. Yet his own theories proved just how strange that comprehensibility could be. Picture a world where time slows down if you move too fast, where the fabric of space bends like a trampoline under the weight of planets, and where two people can experience the same event at different moments, all without breaking any cosmic rules. That's relativity in action. Before Einstein, Newton's clockwork universe seemed unshakable. Gravity was a simple force, time was absolute, and space was just an empty stage. But in 1905, a 26-year-old patent clerk turned physics upside down by asking what would happen if you chased a beam of light. The answer rewrote reality. Special relativity revealed that time and space aren't fixed, they stretch and squeeze depending on how fast you're moving. A clock on a speeding rocket ticks slower than one on Earth. A ruler hurtling past you appears shorter. These aren't illusions, they're the universe's rulebook. Then, 10 years later, general relativity took it further, showing that massive objects like stars don't just pull on each other, they dent spacetime itself. The Earth orbits the Sun because it's rolling along a curve in this invisible fabric, like a marble circling a bowl. Even light, which has no mass, bends around these cosmic dimples. When astronomers first confirmed this during a solar eclipse in 1919, it wasn't just a victory for Einstein, it was proof that the universe played by rules far weirder than anyone imagined. Yet for all its brilliance, relativity left gaps wide enough to drive a quantum paradox through. Einstein's equations break down inside black holes, where gravity becomes infinite, and at the Big Bang's moment of creation, where all physics seems to reset. Worse, relativity and quantum mechanics, the other pillar of modern physics, refuse to speak the same language. Quantum particles ignore spacetime's smooth curves, teleporting through barriers or spinning in two directions at once. Einstein spent his later years haunted by this divide, calling quantum entanglement spooky action at a distance. Today, that spookiness is the frontier. Theories like string theory, loop quantum gravity, and even the holographic principle all grapple with the same question: what stitches these two worlds together? The search for that unified theory isn't just academic nitpicking, it's a hunt for the operating system of reality. If we crack it, we might finally understand what happens at the center of a black hole, or whether time truly exists at the smallest scales. Some theories suggest space itself is pixelated, built from tiny grains a billion trillion times smaller than an atom. Others propose extra dimensions curled up like invisible origami. What's thrilling isn't just the answers we might find, but how they'll reshape our place in the cosmos. Einstein showed us that space and time are fluid. The next revolution could reveal that even infinity isn't what we thought. And somewhere in that unknown, the universe is still whispering its secrets, waiting for the next mind bold enough to listen. Black holes aren't just cosmic vacuum cleaners, they're the universe's most extreme laboratories, bending the rules of reality until they snap. Imagine a place where gravity is so strong, not even light can escape its grip, where time slows to a crawl for an outside observer, yet vanishes entirely for anything crossing the event horizon. These aren't hypothetical scenarios, they're the everyday physics of a black hole, and they're forcing us to confront questions we once thought were reserved for philosophy. What happens to matter crushed into an infinitely dense point? Does information really disappear forever, or is it scrambled into some cosmic code we haven't cracked yet? Just a century ago, black holes were mathematical curiosities Einstein himself doubted they could exist. Now, we've not only proven they're real, we've photographed one. The iconic image of the supermassive black hole at the center of Galaxy M87, released in 2019, showed a fiery ring of light circling a dark void. That shadow isn't just an absence of light, it's a silhouette of spacetime itself, warped into a perfect circle by gravity's relentless pull. But the real surprise: the shadow matched Einstein's predictions almost perfectly, even under conditions far more extreme than he ever tested. It's as if the universe whispered, "You're on the right track, but there's so much more." Inside a black hole, our understanding of physics unravels. At the singularity, the crushed core where density becomes infinite, general relativity's equations explode into nonsense. Quantum mechanics suggests particles might survive in some scrambled form, while string theory hints at hidden dimensions curled up tighter than a knotted thread. Some physicists even speculate that black holes could be portals to other universes, or cosmic factories forging new laws of physics in their depths. The irony: these monstrous destroyers might hold the keys to creation itself. Every photon, every atom they consume carries data about the universe's structure, locked away behind an event horizon like books in a celestial library we can't yet read. The most thrilling part: black holes aren't rare anomalies, they're woven into the fabric of the cosmos. Nearly every galaxy hosts a supermassive one at its heart, including our own Milky Way. Their mergers send ripples through space-time gravitational waves we can now detect with instruments like LIGO. Each collision is a crash course in extreme physics, offering glimpses of how space-time behaves when shredded and stitched back together. And with breakthroughs like Hawking radiation suggesting even black holes aren't eternal, we're left wondering, if these cosmic titans can fade, what other, immutable laws might turn out to be flexible? The more we learn, the clearer it becomes black holes aren't just oddities. They're the universe's way of pushing us to think bigger, dig deeper, and question everything we thought we knew. Dark matter is the universe's greatest magic trick, an invisible hand sculpting galaxies, bending light, and holding the cosmos together without ever revealing itself. We can't see it, touch it, or even detect it directly, yet its fingerprints are everywhere. Take a spiral galaxy like our Milky Way. If you calculate the speed of stars orbiting its edges based on visible matter alone, they should fly off into space like marbles flung from a merry-go-round. But they don't. Something unseen, something massive holds them in place with gravitational glue. That something is dark matter, an enigma making up 27% of everything in existence, outnumbering ordinary atoms 5-1. For decades, scientists have chased this ghost. Some think it's a sea of undiscovered particles, heavier than protons but so shy they rarely interact with normal matter. Others wonder if we've misunderstood gravity itself, that perhaps Einstein's equations need tweaking at cosmic scales. The debate fuels extraordinary experiments. Deep underground, detectors like LUX Zeppelin wait in abandoned gold mines, shielded from cosmic rays, hoping to catch a single dark matter particle bumping into an atom. In space, telescopes like Euclid map the distortion of light from distant galaxies, tracing the gravitational shadows of dark matter's hidden web. Even particle colliders like the Large Hadron Collider smash protons together at near light speeds, hunting for debris that might include dark matter's building blocks. Yet the harder we look, the stranger the puzzle becomes. Some galaxies appear to lack dark matter entirely, while others seem overdosed. There's the Bullet Cluster, where two galaxy clusters collided, and their dark matter, detected via gravitational lensing, sailed right through the crash like a phantom, leaving visible gas behind. If dark matter is particles, why doesn't it behave like anything else in the standard model? If it's modified gravity, why do some cosmic structures fit the theory while others defy it? The stakes couldn't be higher. Crack this riddle, and we might uncover entirely new physics particles that could rewrite textbooks or gravity rules that reshape our cosmic address. Dark matter isn't just a missing piece. It's the scaffolding of reality, the hidden blueprint behind every galaxy, every cluster, every thread of the cosmic web. And until we solve it, we're like mapmakers trying to chart a continent by its shadows, knowing the real terrain lies just beyond our grasp. If dark matter is the universe's hidden scaffolding, dark energy is its silent demolition crew, a mysterious force stretching space itself apart at an ever-increasing speed. Picture a loaf of raisin bread baking in the oven. As the dough expands, every raisin moves away from the others. Now imagine the oven suddenly turns up the heat, and the raisins start fleeing from each other faster and faster. That's our cosmos right now, with galaxies as the raisins and dark energy as the inexplicable heat. What makes this so baffling is that gravity should be slowing this expansion, pulling everything back together. Instead, something we can't see or touch is overpowering gravity itself, shoving galaxies apart like an unseen hand. The discovery of dark energy came from one of the most meticulous cosmic surveys in history. In the late 1990s, two teams of astronomers were studying distant supernova exploding stars so bright they can outshine entire galaxies. These celestial beacons act as cosmic mile markers, letting scientists measure how fast the universe has expanded over billions of years. But the data held a shock. Rather than slowing down as expected, the expansion was speeding up. It was like tossing a ball in the air only to watch it rocket away faster instead of falling back. That revelation earned the researchers a Nobel Prize and left physics scrambling for answers. So what could dark energy be? The leading theory points to the vacuum of space itself, not empty, but fizzing with quantum fluctuations that somehow generate repulsive gravity. Einstein actually predicted this possibility a century ago with his cosmological constant, a term he later called his greatest blunder when the universe seemed static. Turns out he might have been right after all, but there's a catch. Quantum calculations predict vacuum energy trillions of times stronger than what we observe. That staggering mismatch suggests we're missing something fundamental. Alternative ideas are even wilder. Some theorists propose dark energy isn't constant but a dynamic field slowly evolving over time, like an invisible fifth force of nature. Others speculate it's evidence of extra dimensions leaking gravity into our universe, or even a signature of a cyclical cosmos where expansion eventually reverses into collapse. Then there's the multiverse angle. If our universe is one bubble in a froth of others, dark energy's strength might be a random roll of the dice, a fluke that just happened to allow galaxies and us to exist. The implications are staggering. If dark energy's push continues unchecked, distant galaxies will eventually vanish over the cosmic horizon, their light stretched beyond detection. The universe could end not in fire or ice, but in a vast, silent isolation where no future civilizations will ever know galaxies beyond their own existed. Yet for all its bleak potential, dark energy also offers a clue to the deepest questions. Why is the universe structured so precisely for life? How did the initial conditions align so perfectly? Whether it's a cosmological constant, a new physics, or a window into the multiverse, dark energy isn't just tearing space apart, it's tearing open new frontiers of understanding. And somewhere in that mystery lies the next chapter of cosmology, waiting for the bold minds who dare to rethink reality itself. What if everything we call reality, every galaxy, every atom, every moment of history, is just one page in an infinite cosmic library? This isn't science fiction. It's the multiverse hypothesis, a daring idea sprouting from the most perplexing gaps in modern physics. Imagine a frothing sea of universes, each with its own laws, its own version of time, even its own alternate you making different choices. Some might be barren, their physics hostile to life. Others could harbor civilizations stranger than we can dream, and ours just a lucky bubble where the dials happen to land in the sweet spot for stars, planets, and us. The multiverse didn't emerge from wild speculation but from math's cold, hard logic. Take quantum mechanics, where particles exist in multiple states until observed. The many worlds interpretation suggests every quantum decision spawns new branches of reality, one where Schrödinger's cat lives, another where it dies, ad infinitum. Then there's string theory, which requires extra dimensions curled up tighter than a clenched fist. Some models predict 10 to the 500 possible universes, each with unique physics. Even cosmic inflation, the theory explaining the Big Bang's explosive growth, hints at eternal expansion, with distant regions crystallizing into separate universes like ice forming in a supercooled lake. But the multiverse's most tantalizing promise, solving the fine-tuning problem. Why is gravity just strong enough to hold galaxies together but weak enough to allow complex chemistry? Why does the cosmological constant dark energy's fingerprint have such an improbably precise value? If there are infinite universes with randomized laws, odds are one would hit the jackpot. We're not special, we're just the inevitable outcome of probability played out across unfathomable cosmic dice rolls. Critics argue this is philosophy masquerading as science, untestable by definition. Yet clues might lurk in the cosmic microwave background, the afterglow of the Big Bang. Strange cold spots or unusual patterns could be bruises from collisions with other universes. Others hunt for gravitational echoes from before our universe's birth, or anomalies in particle behavior that hint at hidden dimensions. Even if direct proof stays elusive, the multiverse reshapes how we see our place in existence. Suddenly, the constants of nature aren't handed down by divine decree, they're local bylaws in a sprawling cosmic metropolis. The philosophical stakes are dizzying. If every possible outcome happens somewhere, does choice lose meaning? Are failures just alternate timelines where we succeeded? The multiverse doesn't just challenge physics, it redefines identity, destiny, and the very nature of reality. And whether it's ultimately proven or not, this idea already serves a vital purpose, stretching our imagination to cosmic scales, reminding us that the universe, or universes, is far grander, stranger, and more mysterious than we dare assume. At the heart of every atom lies a world that defies all intuition, a realm where particles exist in multiple places at once, where the act of looking changes what's seen, and where two objects can instantaneously influence each other across galactic distances. This isn't fantasy, it's quantum mechanics, the operating system of reality at its smallest scales. Picture tossing a coin in the air. In our everyday experience, it lands as either heads or tails. But in the quantum world, that coin spins in a ghostly superposition, both heads and tails simultaneously, until you catch it and force a decision. That's the essence of Schrödinger's famous cat, neither alive nor dead until the box is opened, exposing the bizarre truth that observation isn't passive. It's an act of creation. The real magic happens when these quantum particles become entangled. Imagine splitting a pair of gloves, one left, one right, and mailing them to opposite sides of the galaxy. Open one package and you instantly know the other's state. But entanglement goes further. The gloves have no defined handedness until observed, at which point both snap into complementary states faster than light could travel between them. Einstein called this spooky action at a distance, and for decades, physicists argued whether such instant connections could exist. Then came experiments like Alain aspects in the 1980s, proving entanglement wasn't a flaw in quantum theory, it was the universe showing its cards. Now scale this up. Could quantum weirdness shape galaxies? The answer might lie in vacuum fluctuations, particle pairs blinking in and out of existence even in empty space. Some theories suggest these fleeting quantum ripples, stretched by the universe's rapid inflation after the Big Bang, seeded the first density variations that grew into galaxies and cosmic webs. Even black holes, those gravitational titans, might preserve quantum information in their event horizons like cosmic hard drives, hinting at a deeper link between the infinitesimally small and the astronomically large. The most tantalizing bridge between quantum mechanics and cosmology, quantum gravity. At the Planck scale, a distance so tiny it makes an atom look planetary, space itself may dissolve into a foamy sea of fluctuating geometries. Here, time could lose all meaning, and wormholes might thread through higher dimensions like stitches in folded fabric. While we lack a full theory to describe this realm, projects like the Event Horizon Telescope are probing black holes, where gravity and quantum effects collide, for clues. Every photon they capture carries whispers of how space-time behaves when shredded to its quantum foundations. What does this mean for us? Quantum mechanics once seemed like an abstract playground for physicists, but its fingerprints are everywhere, from the sunlight warming your skin, a cascade of quantum leaps in solar atoms, to the transistors powering your devices relying on quantum tunneling. Now, as we peer deeper, we're finding quantum rules might not just describe reality, they could actively shape it, from the birth of stars to the fate of the cosmos. The same laws that let electrons teleport through barriers might govern how universes form in a grand multiverse. And that's the ultimate revelation. The universe isn't just stranger than we imagine. It's stranger than we can imagine, with quantum mechanics as our flickering flashlight in the dark. Picture a balloon inflating so rapidly that a dot on its surface streaks from your fingertip to the horizon in less than a trillionth of a second. That's cosmic inflation, the universe's most extreme growth spurt, unfolding in the first sliver of a second after the Big Bang. This wasn't just expansion. It was space itself stretching faster than light could chase it, smoothing the cosmos into the eerie uniformity we see today. Yet for all its explanatory power, inflation feels less like an answer and more like a doorway to deeper mysteries. Why did it start? Why did it stop? And most tantalizingly, could it still be happening beyond the edge of our observable universe, spawning endless bubble realities beyond our reach? The theory's brilliance lies in solving puzzles older telescopes couldn't crack. Why does the cosmic microwave background, the afterglow of the Big Bang, show nearly identical temperatures everywhere, even in regions too distant to have ever exchanged heat? Inflation's answer: those spots were once neighbors, pressed together before space stretched them apart in that explosive initial surge. It also explains why the universe appears flat, Without the dramatic curvature older models predicted, inflation stretched spacetime so thin, any warp became imperceptible, like flattening a crinkled sheet by pulling its edges light years apart. But the clues that validated inflation also revealed oddities. The Planck satellite's ultra-precise maps of the cosmic microwave background showed subtle temperature variations, quantum fluctuations blown up to cosmic scales during inflation, seeding the galaxies and voids we see today. Yet some patterns are strangely lopsided. One hemisphere of the sky has slightly larger fluctuations than the other, and there's a curious cold spot spanning billions of light years that defies easy explanation. Could these be bruises from collisions with other bubble universes during inflation's chaotic peak, or echoes of a pre-inflationary phase we don't yet understand? The wildest implication, inflation might be eternal. Once started, quantum physics suggests it could keep spawning new universe bubbles indefinitely, a multiverse factory where each bubble crystallizes with unique physical laws. Our entire cosmos, with its finely tuned constants enabling life, might just be one lucky roll of the dice in an endless cosmic casino. Some theories even propose that inflation didn't just shape our universe, it was the Big Bang itself, a quantum fluctuation in some primordial spacetime that ignited the chain reaction of creation. Yet for all its grandeur, inflation remains frustratingly elusive. We've detected its predicted gravitational waves only indirectly, through their imprint on ancient light. Future observatories like the LightBird satellite or next-generation ground-based telescopes aim to hunt for primordial B-mode polarization, a swirling pattern in the cosmic microwave background that would be inflation's smoking gun. Others probe the theory's limits by simulating how alternative models might leave different fingerprints on the universe's structure. What's exhilarating isn't just the answers we might find, but how they'll reframe our cosmic story. Inflation paints a universe far more dynamic and interconnected than we once imagined, where the vast web of galaxies traces back to quantum jitters smaller than atoms, and where our entire reality might be one island in an infinite archipelago of universes. As we peer deeper into those first moments, we're not just studying the past, we're glimpsing the hidden architecture of existence itself. Imagine tuning an old radio between stations, catching the hiss of static, a faint whisper of radiation left over from the birth of the universe. That's essentially what astronomers detected in 1965 when Arno Penzias and Robert Wilson stumbled upon the cosmic microwave background, or CMB. At first, they thought the persistent noise in their radio antenna was caused by pigeon droppings, but after scrubbing the equipment and still finding the signal, they realized they discovered something monumental: the afterglow of the Big Bang itself, cooled over 13.8 billion years into a faint microwave hum that permeates every cubic inch of space. This wasn't just leftover heat, it was a time capsule carrying imprints from when the universe was a fiery soup of particles, just 380,000 years old. What makes the CMB so extraordinary isn't just its existence, but its imperfections. When satellites like COBE and Planck mapped this radiation in exquisite detail, they found it wasn't perfectly uniform. Tiny variations, hotspots and cold spots no larger than 1 part in 100,000 dotted the cosmic canvas. These minute fluctuations are the universe's baby pictures, showing where matter was slightly denser or sparser in the primordial plasma. Over eons, gravity amplified those tiny seeds, pulling matter into the galaxies, clusters, and vast cosmic webs we see today. Without those imperfections, the universe would still be a featureless sea of gas, no stars, no planets, no us. But the CMB's secrets go deeper. The precise patterns of those fluctuations act like a fingerprint, revealing the universe's ingredients and how they interact. By measuring the angles between hotspots, scientists confirmed that ordinary atoms make up just 5% of the cosmos, while dark matter accounts for 27% and dark energy 68%. The CMB also carries echoes of the universe's shape, its geometry. When Planck's team analyzed the data, they found space is flat to within a razor-thin margin, meaning parallel lines will never meet or diverge even across billions of light years. This flatness is a smoking gun for cosmic inflation, that explosive expansion in the universe's first moments that stretched spacetime like taffy, smoothing out any curvature. Yet some mysteries linger in the CMB's glow. The axis of evil, an unexpected alignment of large-scale fluctuations that seems to defy statistical randomness, hints at something beyond our current models. Then there's the cold spot, a peculiar region spanning nearly 1 billion light-years where temperatures dip more than theory predicts. Some speculate it could be a bruise from a collision with another universe during inflation, while others suggest it's a cosmic texture defect, a kink in spacetime's fabric left over from the Big Bang. Modern telescopes are pushing even further. Experiments like the Simons Observatory and future missions aim to detect primordial gravitational waves, ripples in spacetime from inflation's violent expansion, that would leave a distinctive swirling pattern in the CMB's polarization. Finding that signal would be like uncovering the universe's first cry, direct evidence of the moment creation switched on. Until then, the CMB remains our oldest and most faithful messenger, a silent broadcast from the dawn of time, reminding us that every structure in the cosmos, from the smallest asteroid to the grandest galaxy, traces back to those faint, flickering whispers in the dark. Time feels like the most dependable constant in our lives, always ticking forward, never backward. But peel back the layers of reality, and this arrow of time becomes one of physics' greatest riddles. At the heart of the mystery lies entropy, the measure of disorder in a system. The second law of thermodynamics states that entropy always increases, which explains why ice melts in your drink but never spontaneously refreezes, or why you remember the past but not the future. Yet this raises a haunting question. If disorder always grows, why was the early universe in such an improbably ordered, low-entropy state? This is the past hypothesis, a puzzle that even Einstein wrestled with, and it hints that time's arrow might not be as fundamental as it seems. Some theories suggest time isn't woven into the fabric of the cosmos at all, but emerges from deeper quantum processes. Picture a deck of cards perfectly ordered by suit and number, an unlikely configuration. Shuffle it, and entropy rises as the cards randomize. The early universe was like that pristine deck, and we're living through the shuffle. But why did it start so orderly? One provocative idea comes from quantum gravity, where time might arise from the entanglement of particles, like a cosmic game of dominoes, where each interaction creates the illusion of a before and after. In this view, time isn't a backdrop to reality. It's a side effect of how quantum systems interact, a flickering shadow cast by deeper, timeless laws. Even stranger is the notion that time's flow might be an illusion, a trick of our limited perspective. Outside a black hole's event horizon, an observer watches a star collapse in slow motion, frozen in time. Yet for someone falling in, time marches on normally until the singularity. Which version is real? Some physicists argue both are, suggesting time is relative not just to speed as in relativity, but to quantum states. The Wheeler-DeWitt equation, a cornerstone of quantum cosmology, famously lacks a time variable altogether, implying that at the universe's most fundamental level, time might not exist. The implications ripple across cosmology. If time is emergent, the Big Bang wasn't the beginning but a phase transition, like steam condensing into water. Some models propose a timeless multiverse where causality loops in ways our linear brains can't grasp. Others suggest entropy's arrow might reverse in a hypothetical big crunch, resetting the cosmic clock. And then there's Boltzmann's wild idea. Given infinite time, random fluctuations could spawn Boltzmann brains, self-aware entities that pop into existence from chaos, complete with false memories of a past. What's clear is that time's arrow isn't just about clocks ticking. It's tied to the universe's structure, the nature of consciousness, and the very possibility of cause and effect. Whether time is fundamental or emergent, its mysteries force us to confront the deepest question of all. Why does anything happen at all? The answer might rewrite not just physics, but our place in the story of existence. Here's a mind-bending thought. What if everything you see, touch, and experience is just an incredibly convincing illusion, like a cosmic version of a high-resolution video game projected from a hidden screen? That's the essence of the holographic principle, a theory so radical it makes parallel universes seem almost mundane. The idea sprouted from an unexpected place, the study of black holes. In the 1970s, physicist Jacob Bekenstein calculated that the maximum amount of information a black hole can contain isn't proportional to its volume, as you'd expect, but to the surface area of its event horizon. It's as if all the data about what falls inside gets compressed into a two-dimensional code on the boundary, like a celestial USB drive. This led to a startling possibility. If black holes encode 3D information on 2D surfaces, could the entire universe work the same way? Imagine the cosmos as a hologram, where every star, planet, and even your morning coffee is really just data etched onto some unimaginably distant shell. The math suggests this isn't just poetic metaphor. In certain theoretical models, it's a necessity. String theory, for instance, describes some universes where gravity emerges from vibrating strings living on a lower dimensional boundary, like shadows cast by a flickering light. Even our everyday physics hints at this. The equations governing quantum mechanics and general relativity simplify beautifully when rewritten in fewer dimensions, as if the universe's complexity is just a smokescreen. But how could this possibly work? Think of a movie screen. The images appear three-dimensional, but they're really just flat pixels. The holographic principle proposes space-time operates similarly. What we perceive as depth might be a projection of information stored at the universe's edge, wherever that may be. This would explain why the fabric of reality seems pixelated at the tiniest scales, with a fundamental limit to how small distances can get. Just as you can't zoom into a JPEG forever without seeing blocks, space-time itself might dissolve into grainy, quantum foam at the Planck length. The implications rewrite the rules of existence. If the holographic principle is true, then black holes don't destroy information. They merely transpose it to another format, solving Stephen Hawking's famous paradox. Time and space might not be fundamental but derived from entangled quantum bits on some vast cosmic hard drive. Even more bizarrely, this could mean our perceived reality is a simulation, not in the sci-fi sense of machines running code, but as a natural consequence of how information structures the universe. Critics argue the principle remains untested, existing mostly in elegant math rather than observable proof. Yet experiments like Fermilab's holometer have hunted for the telltale jitter of spacetime pixels, while others analyze cosmic microwave background patterns for hidden dimensional signatures. Whether the holographic principle holds or not, it's already reshaped how we see reality's scaffolding. After all, if the universe is a hologram, then the most profound truths might not lie in the stars above. but on some unseen surface, we've yet to find a cosmic canvas where all of existence is painted in data. Imagine plucking a guitar string. The vibration creates a note, a unique frequency that defines its sound. Now picture that same principle governing the fabric of reality, where every particle in the universe isn't a point but an unimaginably tiny, vibrating string. The pitch of its vibration determines whether it's an electron, a quark, or even a carrier of gravity. This is the heart of string theory, a vision so ambitious it redefines the building blocks of existence. But here's the twist: these strings don't dance in the 3 dimensions we know. They vibrate in at least 10, with the extra dimensions curled up so tightly they're hidden from view, like the grooves on a vinyl record too fine for the naked eye to see. For decades, physics has been split into 2 warring kingdoms: quantum mechanics, ruling the realm of the infinitesimally small, and general relativity, governing the cosmic scale of stars and black holes. The equations of these domains refuse to speak to each other, creating a rift that's puzzled scientists for a century. String theory emerges as a potential peacemaker, offering a single mathematical framework where gravity and quantum forces harmonize. In this symphony, even the gravitational force isn't a standalone phenomenon. It's just another note in the string's vibrational repertoire. The elegance is intoxicating, a handful of equations describing everything from the spin of an electron to the bending of spacetime. Yet the theory's beauty comes with staggering complexity. Those extra dimensions aren't just abstract math, they're folded into shapes called Calabi-Yau manifolds, intricate 6-dimensional geometries that resemble origami at a scale a billion trillion times smaller than an atom. The way these dimensions curl could determine why we have 3 generations of particles or why gravity is so weak compared to other forces. But here's the catch: we have no way to observe them directly. Some versions of string theory predict a landscape of 10 to the 500 possible universes, each with different physical laws. Ours, with its perfect balance for life, might just be one lucky possibility in an infinite multiverse. Critics argue that a theory without experimental proof is more philosophy than science. They point out that strings, if they exist, would vibrate at energies trillions of times higher than anything our particle colliders can reach. Even the Large Hadron Collider, humanity's most powerful microscope, barely scratches the surface, but supporters counter that mathematics has often guided physics to truths beyond immediate observation. Think of black holes, predicted by equations decades before telescopes found them. Clues might lurk in subtle cosmic signatures, anomalies in the cosmic microwave background, unexpected particle behaviors, or even echoes of higher dimensions in gravitational waves. The debate isn't just academic, it's a battle for the soul of physics. If string theory is correct, we're on the brink of uncovering reality's ultimate code, a theory of everything that could reveal how universes are born, whether time travel is possible, or why existence follows any rules at all. If it's wrong, its mathematical brilliance might still light the path to a deeper truth. Either way, the quest reminds us of science's most humbling lesson: the universe owes us no answers. But as long as there are mysteries, there will be minds daring enough to pluck at the threads of the unknown, listening for the faintest whispers of a cosmic melody. Neutrinos are the universe's ultimate ghosts. Billions pass through your body every second, leaving no trace, as if they weren't there at all. These nearly massless particles, born in the hearts of stars, the fury of supernova, and even the Big Bang itself, barely interact with matter. A neutrino could sail through a light year of solid lead without a single collision. Yet their very elusiveness makes them invaluable cosmic messengers, carrying secrets from the most violent and distant corners of existence. Take a supernova, for example. When a massive star collapses, 99% of its energy erupts not as light, but as neutrinos. In 1987, detectors on Earth caught a fleeting burst of these particles hours before visible light from supernova 1987 reached us. That's because neutrinos escape the star's core unimpeded, while light bounces around in the chaos. Those few captured neutrinos weren't just a scientific triumph. They confirmed that these phantoms can serve as early warning signals for stellar explosions, giving us a front-row seat to cosmic violence we'd otherwise miss. But neutrinos have a quirk that's even more baffling. They shapeshift. As they travel, they oscillate between three types: electron, muon, and tau neutrinos, like a chameleon cycling through colors. This discovery, which earned the 2015 Nobel Prize, proved neutrinos have mass, however minuscule. That tiny mass shouldn't exist under the standard model of particle physics, which long assumed neutrinos were massless. Their oscillation hints at gaps in our understanding, possibly pointing to undiscovered particles or forces lurking beyond current theories. To catch these phantoms, scientists build detectors in some of Earth's most extreme environments. Ice cube buried deep in Antarctic ice watches for the faint blue flashes produced when a rare neutrino collision creates a muon. Other experiments, like Japan's Super Kamiokande, use giant tanks of ultra-pure water to spot similar flashes. These aren't just particle hunts, they're cosmic archaeology. Some neutrinos are relics from the early universe, their energies encoding conditions from epochs we can't otherwise probe. Others, like the ultra-high-energy neutrinos detected by IceCube, trace back to supermassive black holes or colliding galaxies, acting as cosmic GPS markers for the universe's most energetic events. What's at stake isn't just academic. Neutrinos could hold the key to one of physics' greatest mysteries: why the universe is made of matter, not antimatter. The Big Bang should have created equal amounts of both, leaving nothing but energy as they annihilated each other. Yet here we are. Neutrinos, with their subtle matter-antimatter asymmetries, might explain this imbalance. Experiments like Dune Deep Underground Neutrino Experiment aim to test this by firing neutrinos through 800 miles of Earth, watching how they morph along the way. Every neutrino detected is a whisper from the cosmos, a clue wrapped in a riddle. They challenge our theories, connect us to distant cataclysms, and might even reveal why anything exists at all. In their silence, they speak volumes if we're patient enough to listen. Einstein's theory of general relativity gave us a radical new way to think about gravity, not as a force, but as the bending of space-time itself. Picture a trampoline with a bowling ball in the center. The dip it creates is like a star warping space-time, and the marbles rolling toward it mimic planets orbiting. But what happens if you drop two bowling balls onto that trampoline? They spiral inward, collide, and send ripples racing outward. That's gravitational waves in a nutshell, invisible wrinkles in the fabric of reality, generated when massive objects like black holes or neutron stars crash together. For decades, these waves were just math on a page until September 14, 2015, when the Laser Interferometer Gravitational Wave Observatory, or LIGO, caught the faintest whisper of a signal. The detection was a triumph of human ingenuity. Two black holes, each about 30 times the mass of our Sun, had collided over 1 billion light-years away. Their merger unleashed a burst of energy so intense, it briefly outshone all the stars in the observable universe combined. Yet by the time those ripples reached Earth, they'd faded to a distortion smaller than an atomic nucleus. To spot such a minuscule wobble, LIGO lasers raced down 4-kilometer-long vacuum tunnels, bouncing between mirrors so precisely suspended, they're undisturbed by passing trucks or distant earthquakes. When a gravitational wave passes, it stretches one arm of the detector while squeezing the other, creating an interference pattern as delicate as a single note in a cosmic symphony. This discovery didn't just confirm Einstein, it gave astronomy a brand new sense. Before LIGO, we studied the cosmos almost entirely through light-visible radio X-rays. But gravitational waves let us hear the universe, revealing events light could never escape from, like black holes merging in perfect darkness. Already, we've eavesdropped on neutron stars colliding, their crashes spraying gold and platinum into space like cosmic fireworks. Future detectors like the space-based LISA mission or Japan's Kagra will tune into lower frequencies, potentially catching the primordial echoes of the Big Bang itself or the hum of supermassive black holes dancing at the centers of galaxies. The most tantalizing possibilities lie in the unknown. Could gravitational waves uncover exotic objects like cosmic strings, theoretical flaws in space-time left over from the universe's birth? Might they hint at extra dimensions, their presence subtly altering the wave's shape? Every new detection is like opening a window into a realm we've never seen before, where the rules of physics are rewritten in the language of ripples. And just as Galileo's telescope revealed moons around Jupiter or radio astronomy unveiled pulsars, this new sense is poised to expose a universe far stranger, louder, and more dynamic than we ever imagined. The silent cosmos has begun to speak, and we're finally learning how to listen. The universe is unimaginably vast, with billions of galaxies, each containing billions of stars and likely trillions of planets. Given those numbers, the cosmos should be teeming with civilizations, their radio signals crisscrossing the void like cosmic chatter. Yet when we listen, all we hear is silence. This eerie contradiction is the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody? If life is common, why does the universe seem so empty?" The answers we've come up with range from the unsettling to the downright terrifying. One possibility is that intelligent life tends to self-destruct before it can spread across the stars. Climate disasters, nuclear war, runaway artificial intelligence, any of these could act as a great filter, wiping out civilizations before they make contact. If that's true, the silence isn't just puzzling, it's a warning. Another grim idea is that advanced civilizations might avoid broadcasting their presence, fearing hostile neighbors. In a universe where predators lurk in the dark, staying quiet could be the only survival strategy. But not all explanations are doom-laden. Some scientists argue we're simply not looking the right way. Our radio telescopes scan for signals like our own. But what if alien communication uses lasers, neutrinos, or some technology we haven't even imagined? Or perhaps civilizations quickly evolve beyond broadcasting, retreating into virtual realities or harnessing the energy of black holes in ways invisible to us. The universe might be buzzing with activity, just on a scale or frequency we can't yet perceive. Then there's the Drake equation, a formula estimating the number of detectable civilizations in our galaxy. Plug in optimistic numbers, lots of habitable planets, high odds of life arising, and the Milky Way should be packed with intelligent species. Yet the silence forces us to reconsider those assumptions. Maybe life is rarer than we think, or intelligence is a fluke, not an inevitability. The most haunting answer of all, we might truly be alone. Earth could be a cosmic accident, a one in a trillion spark of consciousness in an otherwise lifeless void. If so, the responsibility to preserve and spread life falls entirely on us. The Fermi paradox isn't just about aliens, it's a mirror forcing us to confront our place in the universe and the fragility of our own existence. Whether the silence is a warning, a puzzle, or a tragic reality, it compels us to look deeper, listen harder, and wonder if we'll ever find an answer. Among the countless stars dotting the night sky, hidden in their glow, are worlds beyond our wildest imaginings, planets orbiting distant suns, some perhaps cradling oceans, atmospheres, or even life. Since the first exoplanet discovery in 1995, astronomers have catalogued over 5,000 of these alien worlds, and the tally grows almost daily. The real marvel isn't just their existence, but their staggering variety: puffy gas giants denser than iron, rogue planets drifting untethered from any star, and most tantalizing of all, rocky planets nestled in the Goldilocks zone, where temperatures might allow liquid water to pool on their surfaces. These aren't just scientific curiosities, they're mirrors reflecting possibilities, some showing us what Earth could have been, others hinting at what it might yet become. Take Kepler 452b, a world nicknamed Earth's cousin. Orbiting a sun-like star every 385 days, it was the first near-Earth-sized planet found in the habitable zone of its star. Then there's TRAPPIST-1's 7 rocky planets, 3 of which orbit in the sweet spot where water could flow. But the game-changer is the James Webb Space Telescope, or JWST, whose infrared eyes can dissect the light filtering through exoplanet atmospheres, hunting for chemical fingerprints like methane, oxygen, or even industrial pollutants. Imagine the moment JWST data reveals an atmosphere rich in oxygen, a gas that, on Earth, is almost entirely produced by life. Would that be proof of alien forests, oceans brimming with plankton, or something stranger? Yet the search is fraught with cosmic false alarms. Oxygen can arise from non-biological processes, like sunlight splitting water molecules. Methane, often belched by microbes on Earth, also spews from volcanoes. The real smoking gun would be a mix of gases out of equilibrium, say, oxygen and methane coexisting, which on Earth happens only because life constantly replenishes them. Even then, caution reigns. As astronomer Carl Sagan warned, extraordinary claims require extraordinary evidence. Beyond biosignatures, exoplanets challenge our cosmic perspective. Consider that most stars in our galaxy are red dwarfs, dim, cool, and prone to violent flares. Could life adapt to such environments, clinging to existence under a perpetual twilight? Or ponder eyeball Earths, tidally locked planets where one side always faces its star, creating a scorching day side and frozen night side, with a narrow ring of twilight in between where life might huddle. The more we discover, the clearer it becomes. Earth isn't the template for habitability, just one possibility in a universe that thrives on diversity. The ultimate question isn't just, are we alone? But what does life's diversity look like across the cosmos? With next-generation telescopes like the Habitable Worlds Observatory on the horizon, we might soon have an answer, one that could redefine our place in the universe. Whether that answer comes as a whisper or a shout, the very act of searching reminds us of something profound. In a universe teeming with worlds, the most remarkable discovery might be how rare or how common our own pale blue dot truly is. Life as we know it clings to every imaginable niche on Earth, from scalding volcanic vents to frozen Antarctic lakes, from acidic rivers to the crushing depths of the ocean floor. These extremophiles, organisms thriving in conditions once thought lethal, have rewritten the rules of where life can exist. If microbes can survive inside radioactive waste or metabolize sulfur in pitch-black caves, why couldn't life gain a foothold in the icy cracks of Europa or the methane lakes of Titan? Astrobiology, the study of life's potential beyond Earth, isn't just about little green aliens, it's about uncovering the universal principles that might govern biology anywhere in the cosmos. Take Mars, our most tantalizing neighbor. While its surface today is a barren, radiation-scorched desert, the Perseverance rover is scouring Jezero crater for signs of ancient microbial life. Billions of years ago, this was a river delta, its waters potentially teeming with organisms. The rover's drill collects samples that future missions will return to Earth, hunting for fossilized bacteria or chemical traces only life could leave behind. Even more intriguing are Mars's underground aquifers, hinted at by liquid water detected beneath the South Pole. If life exists there now, it might resemble Earth's deep subsurface microbes, surviving without sunlight by feeding on rocks and minerals. Then there's Europa, Jupiter's icy moon. Beneath its frozen crust lies a global ocean twice the volume of Earth's seas, kept liquid by tidal forces flexing its core. The upcoming Europa Clipper mission will map this hidden realm, probing plumes that erupt from cracks in the ice, potential shortcuts for sampling the ocean without drilling miles down. What might thrive in such a place? On Earth, ecosystems flourish around hydrothermal vents, where chemosynthetic bacteria form the base of a food web that includes giant tube worms and blind shrimp. Europa's ocean could host similar communities, powered not by sunlight but by chemical energy leaching from its rocky seafloor. But what if life elsewhere isn't just hidden? What if it's fundamentally different? We assume life requires carbon, water, and DNA, but alternative biochemistries might be possible. On Titan, where temperatures plunge to minus 290 degrees Fahrenheit, liquid methane takes water's role. Could there be cells with membranes made of nitrogen compounds, floating in hydrocarbon lakes? Or consider Venus's clouds, where acidic droplets might harbor microbes adapted to a sulfuric acid atmosphere. Even silicon, which bonds similarly to carbon, has been proposed as a potential backbone for alien life forms. The search stretches beyond our solar system. Telescopes like JWST analyze exoplanet atmospheres for biosignatures, gases like oxygen or methane that, in the right combinations, hint at biological activity. But the real challenge is distinguishing true signs of life from geological or chemical false alarms. A single detection won't be enough. Scientists will need patterns, context, and perhaps even imagery to say with confidence that we're not alone. Astrobiology forces us to confront the deepest questions. What makes something alive? Is life a cosmic fluke or an inevitable outcome of chemistry given the right conditions? Every new discovery, whether a microbe in a Martian rock or a strange molecule in Titan's haze, brings us closer to answering whether Earth's vibrant biosphere is unique or just one thread in a vast interstellar tapestry of life. The universe has already shown us how creative it can be with stars, planets, and black holes. Why not biology too? What if everything around you, the screen you're staring at, the chair beneath you, even the stars overhead, isn't real in the way you think? This isn't a plot from a sci-fi movie. It's the simulation hypothesis, a serious philosophical argument that's gained traction among technologists and physicists alike. The core idea is startlingly simple. If advanced civilizations could one day create hyper-realistic simulations of conscious beings, and if those simulated beings could run their own simulations, then statistically, the odds suggest we're far more likely to be living inside one of those nested realities than in the original, base universe. It's a modern twist on an ancient question: how do we know our reality is the real one? But this time, it's dressed in the language of quantum physics and computing power. The argument gained mainstream attention when philosopher Nick Bostrom formalized it in 2003. He proposed that at least one of three possibilities must be true. Either civilizations like ours never reach the technological capability to create such simulations, they choose not to run them, or we're almost certainly living inside one. The first two options rely on speculative limitations, either self-destruction or ethical restraint, while the third leans on pure probability. If even a fraction of advanced civilizations run ancestor simulations, the number of simulated minds would dwarf biological ones, making our own odds of being real vanishingly small. But this isn't just abstract philosophy. Quantum mechanics adds eerie supporting evidence. At the smallest scales, particles exist in fuzzy superpositions until observed, as if the universe is rendering details only when needed to save processing power. The pixelation of spacetime at the Planck length could hint at a cosmic resolution limit, much like a video game's polygons. Even glitches in the matrix, like déjà vu or quantum tunneling, where particles phase through barriers, take on new meaning through this lens. Critics, though, are quick to point out the hypothesis's flaws. For one, it's unfalsifiable. There's no experiment to prove we're not in a simulation, making it more metaphysics than science. Others argue that simulating consciousness at the atomic level would require energy beyond any plausible future tech. And then there's the recursion problem. If we're simulations and our simulators are too, who's at the top? An infinite stack of realities collapses into logical absurdity, yet the hypothesis forces profound questions. If we're code in some alien supercomputer, does free will exist, or are we following predetermined algorithms? Could glitches be exploited to hack our reality? And if simulations can spawn simulations, what does that say about the nature of creation itself? Whether you find the idea thrilling or unsettling, it undeniably reframes our place in the cosmos. After all, if this is a simulation, the real mystery isn't just who's running it, but why. What if consciousness isn't something the universe creates, but something it's built from? This radical idea flips the traditional view of awareness on its head. Instead of consciousness emerging from complex brains, some theories propose it's woven into the fabric of reality itself, a fundamental property like mass or charge. At the heart of this concept lies panpsychism, the philosophy that even elementary particles possess a whisper of experience. Imagine an electron not just as a buzzing point of energy, but as a tiny subject feeling the barest glimmer of what it's like to exist. Scale this up, and the entire cosmos might thrum with a kind of proto-mind, a vast network of interconnected awareness. The evidence for such thinking isn't purely philosophical. Quantum mechanics adds eerie fuel to the fire. In the double-slit experiment, particles behave differently when observed, as if the act of measurement collapses their fuzzy possibilities into concrete reality. Some interpretations suggest consciousness plays an active role, that the universe requires an observer to decide its state. Nobel laureate Eugene Wigner even speculated that quantum effects couldn't resolve without a mind present. While mainstream physics often sidesteps this idea, it raises a haunting question. Is the universe not just knowable, but somehow knowing? Information theory deepens the mystery. From black holes preserving data on their event horizons to the holographic principle suggesting reality might be a projection from a two-dimensional surface, there's growing evidence that the cosmos operates like a vast self-processing network. If information is the fundamental currency of existence, could awareness be how that information feels from the inside? Think of your own brain, a 3-pound lump of tissue somehow generating the rich movie of your lived experience. What if that's not a miracle, but a local intensification of something universal? The implications ripple across science and spirituality alike. Indigenous cosmologies have long spoken of animate mountains and sentient rivers, while cutting-edge theories like integrated information theory attempt to quantify consciousness mathematically. Even the eerie fine-tuning of the universe, those precise constants allowing for stars, planets, and life, hints at something startling. Could a cosmos capable of understanding itself be the point all along? Whether you find this idea inspiring or unsettling, it forces a profound shift. We might not be thinkers in a dead universe, but thoughts in a living one. Consider a universe where gravity was slightly stronger, stars would burn too fast for life to evolve, or one where the nuclear force was weaker, atoms couldn't form. The precision of these constants isn't just impressive, it's unnerving. Change any one of them by a fraction, and the cosmos becomes a barren wasteland. This eerie perfection is the heart of the anthropic principle, the idea that our universe's laws appear fine-tuned because, well, we're here to notice them. If conditions weren't just right, no one would be around to ask why. But is this a profound insight or a cosmic shrug? One way to sidestep the design debate is the multiverse. Imagine endless bubble universes, each with random physical constants. Most are lifeless voids, but a rare few hit the jackpot Goldilocks zones where particles, forces, and energies align to forge galaxies, planets, and eventually conscious minds. In this view, we're not special, we're just the lucky winners of a cosmic lottery. The catch, if other universes are permanently beyond our reach, the multiverse becomes less a scientific theory and more a philosophical escape hatch. Yet there's a deeper layer. The anthropic principle isn't just about physics, it reshapes how we think about existence itself. Take carbon, the backbone of life. Its abundance relies on a precise resonance in stellar nuclear reactions, a fluke so unlikely it feels orchestrated. Even the vacuum energy, that mysterious dark energy pushing the cosmos apart, is fine-tuned to 1 part in 10 to the 120. That's like throwing a dart across the observable universe and hitting a bullseye the size of an atom. Coincidence strains credulity. Philosophers and theologians have long seized on this fine-tuning as evidence of intentional design. But science offers alternatives. Some theorists propose self-creating universes, where the laws of physics bootstrap their own existence through quantum loops or higher dimensional brains. Others wonder if consciousness somehow retroactively influences the universe's initial conditions, a wild twist where observers create the very reality that creates them. The anthropic principle's real power lies in its humility. It forces us to confront the limits of our perspective. We can't ask why the universe is life-friendly without acknowledging that unfriendly ones leave no one to ask. Whether you see this as a tautology or a revelation, it reframes the ultimate question. Are we the universe's purpose or just its accident? The answer, like the cosmos itself, might be stranger than we dare imagine. Time bends in ways that defy common sense, twisting into loops that could, in theory, let you shake hands with your past self or witness dinosaurs roaming Earth. The idea isn't just science fiction, it's rooted in real physics. Take wormholes, those hypothetical tunnels through space-time predicted by Einstein's equations. If one end of a wormhole were accelerated to near light speed or placed near a black hole, time dilation would cause clocks at each end to tick at different rates. Step through and you might emerge centuries in the past, but there's a catch. Wormholes require exotic matter with negative energy to stay open, a substance we've never observed. Even if they exist, the universe might enforce a cosmic censorship, collapsing the tunnel before paradoxes can unfold. Then there are cosmic strings, infinitely thin threads of energy left over from the Big Bang, thinner than an atom yet denser than a neutron star. If two of these strings moved past each other at near light speed, They could warp spacetime so severely that closed time-like curves would form, allowing a path back to your own past. The math checks out, but the engineering is laughably beyond us. Imagine trying to harness cosmic superstrings like subway lines to the past, but the weirdest time travel clues come from quantum mechanics. In experiments, particles seem to retro-cause their own past, changing behavior based on measurements made later. This isn't just academic. It suggests the universe might tolerate some backward-in-time influence, at least on tiny scales. The quantum grandfather paradox plays out differently than the classic version. Instead of erasing your existence, quantum rules might just nudge probabilities, making some timelines more likely than others. The real barrier isn't just physics, it's logic. If time travel were possible, where are the tourists from the future? Maybe they're hiding, or maybe paradoxes act as self-correcting mechanisms, snipping off inconsistent timelines like cosmic error checking. Or perhaps, as Hawking quipped, the universe simply refuses to tolerate time travelers, deploying some yet unknown law to keep history tidy. Until we crack quantum gravity or stumble upon a wormhole in the lab, time travel remains the ultimate what if. But the fact that it's even a scientific debate at all proves how strangely time behaves when you push it to its limits. The universe's final act hinges on a cosmic tug of war we can't yet see the end of. On one side, dark energy keeps pushing galaxies apart with ever-increasing speed, as if space itself has a hidden accelerator pedal stuck to the floor. If this continues, trillions of years from now, stars will burn out, black holes will evaporate, and the cosmos will fade into a quiet, frigid darkness, a state physicists call heat death. Picture an endless void where the temperature everywhere approaches absolute zero, and no energy remains to spark even a single chemical reaction. It's not an explosion or a collapse, but the slowest, most gentle end imaginable, a universe exhaling its last breath into infinite stillness. But heat death isn't the only possible finale. What if dark energy weakens over time or reverses into a cosmic pull? Gravity might eventually halt the expansion, dragging all matter back together in a catastrophic big crunch. Galaxies would collide, temperatures soar, and space itself contracts until every atom smashes into a singularity, a mirror image of the Big Bang but running in rewind. Some theories even suggest this could trigger a new cycle of creation, like a phoenix universe rising from its own ashes. The math allows for it, but here's the catch. Current observations show dark energy's push is winning. The crunch scenario grows less likely with every passing discovery, unless we've misunderstood gravity itself. Then there's the more unsettling possibility, the Big Rip. If dark energy's strength increases over time, it wouldn't just push galaxies apart, it would tear them and eventually atoms apart at the seams. First, galaxy clusters would be ripped from one another, then individual stars from their galaxies. In the final moments, even atomic nuclei would be shredded as the repulsive force overcomes the strong nuclear force binding them together. The universe wouldn't just end, it would unravel piece by piece in a crescendo of destruction. But perhaps the strangest doomsday is vacuum decay. Imagine the fabric of reality is like ice on a frozen lake stable, but not the lowest energy state possible. If a quantum fluctuation triggers a phase transition to a truer vacuum, a bubble of new physics could expand at light speed, rewriting the laws of nature as it goes. One moment the universe operates as usual, the next chemistry, light, even the structure of matter might cease to exist in any recognizable form, the chilling part. This could happen at any instant with no warning anywhere in the cosmos. What binds these scenarios together is their sheer inevitability. Whether it's the slow fade of heat death or the violent reset of a big crunch, the universe's fate forces us to confront the fleeting nature of existence. Civilizations rising billions of years from now might gaze at an empty sky, their telescopes capturing only the dim remnants of stars long dead. All traces of our era, every monument, every memory will have dissolved into the void. Yet there's a strange comfort in this. The universe doesn't end with a whimper or a bang because of some flaw or punishment. It's simply following the logic of its own birth. And in that inevitability, there's a kind of poetry, a reminder that meaning isn't found in permanence, but in the brief, brilliant spark of now. Crossing the vast emptiness between stars isn't just an engineering challenge. It's a test of human ingenuity against the universe's harshest constraints. Take Alpha Centauri, our closest stellar neighbor at 4.37 light-years away. With today's fastest spacecraft, the journey would take over 70,000 years. That's longer than all of recorded human history just to reach the next-door solar system. But scientists aren't backing down. Some proposed generation ships massive arcs where entire civilizations would live and die during the voyage, treating the ship itself as a permanent homeland rather than a vessel. These wouldn't just be transports but self-contained ecosystems, recycling every molecule of air and water while hurtling through the void. The psychological and biological hurdles are staggering. How do you maintain genetic diversity over centuries, prevent societal collapse in a closed environment, and most hauntingly, would the descendants of the original crew still care about a planet their ancestors left behind? Then there's the audacity of Breakthrough Starshot, a plan to fling gram-sized nanoprobes toward Alpha Centauri at 20% the speed of light using Earth-based lasers. These featherweight explorers would carry cameras, sensors, and tiny thrusters, beaming back data as they zip past alien worlds. The engineering is mind-bending, sails thinner than a human hair pushed by photons, surviving decades of bombardment by interstellar dust. A single grain of sand could vaporize a probe instantly, yet if it works within our lifetimes, we could receive close-up images of exoplanets, potentially spotting oceans, continents, or even signs of life. The project's founder, Yuri Milner, calls it humanity's first leap into the interstellar ocean. But what if we could cheat distance entirely, enter warp drives, not the sci-fi fantasy kind, but real theoretical models like Miguel Alcubierre's 1994 proposal? By compressing spacetime in front of a ship and expanding it behind, the vessel could effectively ride a wave through the cosmos without breaking Einstein's speed limit. The catch: it requires exotic matter with negative energy density, something we've never observed. NASA Eagleworks lab has experimented with microscopic warp field interferometers, but the energy demands remain astronomical. Even if feasible, a warp bubble might unleash deadly radiation or obliterate anything at the destination upon arrival. Wormholes offer another tantalizing shortcut: bridges through spacetime's folds predicted by general relativity. Picture the universe as a sheet of paper. Bend two distant points together, and a wormhole could connect them like a pencil stabbing through the page. The problem: stabilizing one would require the same exotic matter as warp drives, and quantum effects might slam it shut instantly. Some theories suggest naturally occurring microscopic wormholes could have formed in the early universe's chaos, but finding or creating a traversable one remains firmly in the realm of speculation. The urgency behind these dreams isn't just exploration, it's survival. Sooner or later, Earth will face an existential threat, whether a rogue asteroid, gamma-ray burst, or our own environmental mismanagement. Interstellar travel isn't merely about curiosity, it's about backing up the human experiment. The distances are cruel, the physics daunting, but the alternative, putting all our eggs in one planetary basket might be the riskiest gamble of all. Every blueprint, from generation ships to laser-propelled dots, is a vote of confidence that humanity's story shouldn't end with Earth. The stars may be silent now, but they won't stay out of reach forever. The night sky hums with countless stars, each potentially hosting civilizations as curious as ours. For over 60 years, scientists have listened for whispers of alien intelligence, scanning radio waves, analyzing light patterns, and hunting for anomalies that scream artificial. This passive search, known as SETI, the search for extraterrestrial intelligence, operates on a simple premise. If advanced societies exist, they might leak signals into space, whether intentional broadcasts or accidental technosignatures like city lights or industrial byproducts. The infamous WOW signal, a 72-second burst of radio waves detected in 1977, remains the closest we've come to a potential hello from the cosmos. But silence dominates, leaving us wondering, is no one out there, or are we listening wrong? Then there's METI, messaging extraterrestrial intelligence, the controversial cousin of SETI. Instead of waiting, METI advocates actively beaming messages into space, targeting nearby stars with mathematical sequences, music, or even DNA blueprints. The idea sparks fierce debate. On one side, proponents like astronomer Douglas Vakoch argue that humanity's greatest discoveries came from taking risks, from Magellan's voyages to the Apollo missions. If we want contact, they say, we must raise our voice above the cosmic static, but critics, including Stephen Hawking, warn that broadcasting our presence could invite catastrophe. Advanced civilizations might view us as ants beneath a boot, or worse, as a resource to exploit. The Dark Forest hypothesis, inspired by sci-fi but rooted in game theory, suggests the universe is silent because every species hides, fearing predators. The ethical lines blur further when you consider who speaks for Earth. Early broadcasts, like the Arecibo message sent in 1974, were crafted by small teams without global consensus. Today, private initiatives like METI International beam signals without oversight, while organizations like the International Academy of Astronautics draft shaky protocols for post-detection diplomacy. Should a handful of scientists decide humanity's fate, and what if we're not the ones sending, what if we're the recipients? Imagine picking up a signal tomorrow. Would governments reveal it or hoard the knowledge? History suggests the latter. When astronomers detected the first fast radio bursts, some data sat classified for years. Perhaps the greatest irony is how fragile our own technosignatures have become. As Earth shifts from radio towers to fiber optics, our electromagnetic footprint shrinks, leaving a narrower window for aliens to notice us. Future archaeologists sifting through the cosmos might spot our mid-20th century radio surge, then silence, a fleeting blip. Meanwhile, new telescopes like the Vera Rubin Observatory scan for laser pulses or Dyson spheres, while AI sifts through data for patterns too subtle for human eyes. The search evolves, but the core question lingers. In a universe that's either teeming with life or eerily empty, do we dare shout into the dark? The answer depends on whether we see the cosmos as a community or a battlefield, and whether curiosity outweighs fear. At the heart of modern physics lies an impossible marriage, two titanic theories that refuse to speak the same language. On one side, quantum mechanics governs the subatomic realm with probabilistic fuzziness, where particles exist in multiple states until observed. On the other, Einstein's general relativity paints gravity as the graceful curvature of space-time, bending planets and light alike. Both theories work flawlessly in their domains, but when forced together, like at the singularity of a black hole or the first moments of the Big Bang, their equations explode into nonsense. This isn't just academic nitpicking, it's a crisis at the foundation of reality, and solving it might require rewriting the rules of existence itself. Enter loop quantum gravity, one of the boldest attempts to stitch these worlds together. Picture spacetime not as a smooth continuum, but as a fabric woven from tiny, indivisible loops. Think of a mesh so fine it appears seamless from afar. These loops intersect at nodes, creating a network where area and volume are quantized, meaning space itself comes in discrete chunks. The implications are staggering. No singularities, no infinite densities, just a cosmic pixelation at the Planck scale. Black holes wouldn't crush matter into oblivion, but transform it into a dense knot of these loops, potentially preserving information in a way that satisfies quantum rules. Even the Big Bang might not have been a true beginning, but a rebound from a previous universe's collapse, a cosmic bounce written in the language of spinning loops. But loop quantum gravity isn't the only contender. Causal sets take a radically different approach, arguing that spacetime is fundamentally a collection of discrete events linked by cause and effect. Imagine the universe as a vast, growing network where each point connects only to its immediate influences, like a cosmic family tree. Time emerges from the sequence of these connections, and space from their arrangement. This minimalist framework elegantly sidesteps infinities, no need for infinitesimal points or infinitely curved geometries. Yet it raises its own puzzles. How does the smooth spacetime we experience emerge from this abstract web? And why does it seem to obey Einstein's equations so precisely? Meanwhile, string theory, often seen as quantum gravity's flashier rival, proposes that particles aren't dots but vibrating strings, with their harmonies dictating forces and matter. It elegantly includes gravity by default, but at a cost, requiring 10 or 11 dimensions, most curled up beyond detection. The math is breathtaking, but critics argue it's more art than science until testable predictions emerge. Then there's asymptotic safety, a lesser-known idea suggesting gravity might behave like a fractal, looking the same at all scales if you tweak its parameters just right. The stakes couldn't be higher. Success wouldn't just tidy up equations, it would unlock the universe's deepest secrets, what really happens inside a black hole. Did time exist before the Big Bang? Is spacetime fundamental or just a useful illusion? Each approach offers tantalizing glimpses, but the full picture remains maddeningly out of reach. Experiments might one day catch whispers of quantum gravity in the faint echoes of merging black holes or the afterglow of the Big Bang. Until then, theorists wage a quiet war of equations, each convinced their path leads to the promised land where quantum and gravity finally shake hands. The winner won't just claim a Nobel Prize, they'll redefine reality itself. When a massive star exhausts its fuel and collapses, it doesn't always become a black hole. Sometimes it leaves behind a neutron star, nature's most extreme pressure cooker. Imagine squeezing the mass of our sun into a sphere the size of Manhattan, where gravity crushes atoms so violently that electrons merge with protons, forming a seething ocean of pure neutrons. The result is matter so dense that a single sugar cube's worth would weigh as much as Mount Everest. This isn't just theoretical. In 2017, the collision of two neutron stars was detected both in gravitational waves and light, a cosmic first that confirmed these objects as the universe's ultimate alchemists. The explosion forged over an Earth's mass in gold and platinum, scattering precious metals across space like a celestial jewelry explosion. But neutron stars aren't just dense, they're also cosmic dynamos. Some, called pulsars, spin hundreds of times per second, beaming lighthouse-like jets of radiation across the galaxy. These aren't gentle rotations. The fastest known pulsar, PSRJ 1748-2446 AD, whips around at nearly 43,000 miles per hour at its equator. Then there are magnetars, neutron stars with magnetic fields so intense they'd erase credit cards from halfway to the moon. These fields can crack the star's crust, triggering starquakes that release bursts of gamma rays, some of the brightest flashes in the universe. In 2004, a magnetar flare 50,000 light-years away briefly outshone the full moon, despite being smaller than a city. What's truly mind-bending is how neutron stars push physics to its breaking point. At their cores, the pressure might be so extreme that neutrons dissolve into a soup of quarks, creating a state of matter that can't exist anywhere else. Some theories even suggest strange stars could form where strange quarks, a heavier cousin of up and down quarks, dominate. These exotic possibilities aren't just curiosities, they're laboratories for studying quantum chromodynamics, the rules governing how quarks interact. By observing neutron stars, we're essentially running experiments at energies impossible to replicate on Earth. The echoes of neutron star collisions also ripple through spacetime itself. When LIGO detected gravitational waves from merging neutron stars in 2017, the event didn't just confirm Einstein, it opened a new era of multi-messenger astronomy. For the first time, we could compare gravitational waves with visible light, X-rays, and even gamma rays, piecing together a holistic picture of cosmic violence. These collisions are so energetic they warp spacetime like a trampoline hit by a cannonball, sending out ripples that subtly stretch and squeeze everything in their path. Yet for all their ferocity, neutron stars are remarkably precise. Pulsars spin with such regularity that their flashes rival atomic clocks, making them ideal cosmic navigation beacons. Some scientists have proposed using pulsar timing arrays to detect low-frequency gravitational waves from supermassive black hole mergers, turning these dead stars into galaxy-scale detectors. Others dream of harnessing their extreme conditions to test quantum gravity or even dark matter theories. Neutron stars are more than stellar tombstones, they're Rosetta Stones, decoding the universe's most violent and enigmatic processes. From forging the gold in your wedding ring to bending the fabric of reality, these cosmic diamonds prove that death in the universe isn't an end, but a transformation into something even more extraordinary. White holes are the universe's ultimate cosmic rebels where black holes devour everything. White holes spit it all back out. Imagine a black hole running in reverse, instead of an event horizon that traps light forever. These theoretical objects would have an impassable boundary that nothing can enter, only escape. The math allows it. Einstein's equations don't care if time flows forward or backward. And if you flip a black hole's timeline, you get a white hole. But here's the catch. While black holes form naturally when massive stars collapse, white holes would need to emerge fully formed, like a cosmic magician pulling a rabbit from an empty hat. One tantalizing idea is that white holes could be the afterlife of black holes. Some theories of quantum gravity suggest that when a black hole evaporates via Hawking radiation, it doesn't just vanish, it rebounds as a white hole, transforming into a fountain of matter and energy. Picture a black hole shrinking over eons until it reaches a critical point, then erupting like a geyser, spewing out everything it ever consumed. This would solve the infamous information paradox, ensuring the universe doesn't lose data forever. But there's no evidence yet, and the timescales are mind-bending. A solar mass black hole would take longer than the current age of the universe to evaporate. Then there's the wilder speculation: could the Big Bang itself have been a white hole? If our universe burst forth from an ultra-compressed state, the sudden release of energy fits the white hole's profile. Some cosmologists even toy with the idea that white holes could be hiding in plain sight as dark matter. if these objects are scattered throughout galaxies, ejecting invisible particles or energy, their gravitational pull might explain the missing mass we've been chasing for decades. But why haven't we seen one? White holes would be spectacularly bright, flinging radiation and matter into space. One theory suggests they self-destruct almost instantly, collapsing into black holes the moment they form. Others argue they're cloaked behind event horizons of their own, or that they exist in regions of spacetime cut off from our own. The truth is, white holes remain a dazzling, what if a reminder that the universe's rulebook might still have pages we haven't turned yet. Whether they're real or just mathematical ghosts, they challenge us to think differently about time, gravity, and the very nature of existence. After all, if black holes teach us how spacetime bends, white holes might teach us how it breaks. The silence of the cosmos isn't just puzzling, it might be a warning. Fermi's paradox asks why, in a universe teeming with potential habitats, we hear nothing but static. One chilling answer lies in the concept of the Great Filter, an invisible barrier that prevents life from reaching the stars. The question isn't just whether the filter exists, but where it's positioned in the timeline of civilizations. If it's behind us, if the emergence of intelligent life is astronomically rare, then we've already beaten the odds. But if it's ahead, lurking in our future, that means every civilization that came before us hit a wall they couldn't overcome. And if that's true, what's waiting for us? Consider the candidates for this existential hurdle. Nuclear war once seemed the obvious contender, a flash of hubris erasing civilizations in hours. But today, new threats loom. Artificial intelligence could outpace human control, not through malice, but by pursuing goals misaligned with our survival. Imagine an AI designed to optimize crop yields deciding that humans consume too many resources, or one tasked with curing disease viewing humanity itself as the pathogen. Then there's bioengineering, where a single lab accident or weaponized virus could spiral into a global catastrophe. Even climate change, often framed as a slow burn, might trigger cascading collapses, food shortages, mass migrations, and wars over dwindling resources. But the filter might not be technological at all. It could be sociological. Civilizations may inevitably reach a point where their tools outstrip their wisdom, where tribalism or short-term thinking prevents cooperation on the scale needed to survive. Look at our own struggles with pandemics or climate accords. If a species can't unite to solve planet-sized problems, how could it ever navigate interstellar challenges? Alternatively, the filter could be existential boredom, a future where virtual realities offer infinite pleasure, and no one bothers to look up at the stars anymore. Here's the twist: the Great Filter isn't just a threat, it's a test. If we're aware of it, we might dodge it. That's why projects like biosecurity labs, AI alignment research, and asteroid detection systems aren't just practical, they're cosmic necessities. Every decision we make about climate, governance, or technology isn't just about the next election cycle. It's about whether humanity becomes a fleeting spark or a lasting flame. The silence of the universe might be a tombstone, but it could also be a challenge. And if we're the first to hear it, that means we might also be the first to break through. Deep in the Milky Way's halo, ancient stars flicker like cosmic time capsules, their light carrying chemical fingerprints from an era before Earth existed. These metal-poor stars, forged when the universe was less than 1 billion years old, contain barely any elements heavier than hydrogen and helium. Their pristine atmospheres are laboratories for studying the universe's infancy, revealing how the first supernova seeded space with carbon, oxygen, and iron. Take HD 140,283, nicknamed the Methuselah star. Its iron content is just 1% of the Sun's, suggesting it formed from nearly pure Big Bang material. By analyzing such stars, astronomers have reconstructed a pivotal chapter in cosmic history, the moment when the sterile early universe became chemically enriched enough to build planets and life. But stars aren't the only relics whispering secrets. Dwarf galaxies like Segway 1, barely visible against the night sky, behave like living fossils. Their sluggish star formation and primitive compositions suggest they're survivors from the cosmic dark ages, when the first starlight pierced the fog of hydrogen gas. Meanwhile, hypervelocity stars catapulted across the galaxy by supermassive black holes trace gravitational events that unfolded billions of years ago. These stellar outlaws act as cosmic breadcrumbs marking paths of ancient galactic collisions. The most dramatic chapters are written in galactic wreckage. When the Milky Way and Andromeda collided with smaller galaxies, their gravitational tides stretched victim stars into streams, luminous rivers like the Gaia Sausage, a remnant of a dwarf galaxy devoured 8 to 10 billion years ago. By simulating these mergers, astronomers can rewind the chaos, testing how galaxies grow by cannibalizing their neighbors. Even the elements under our feet tell a story. Gold's rarity hints at its violent origins. Most wasn't forged in ordinary supernova, but in neutron star collisions, events so rare that all the gold in the universe could fit into a single cubic kilometer. This cosmic archaeology isn't just about the past, it's a key to the future. By understanding how galaxies mature, we can predict the Milky Way's fate when it merges with Andromeda in 4 billion years. The universe's biography, etched in starlight and gravity waves, reminds us that every atom in our bodies was once part of something grander. A star's fiery heart, a galaxy's dance, or the explosive death that made our existence possible. From black holes bending spacetime to quantum particles defying logic, we've journeyed through a cosmos that constantly reinvents our understanding of reality. These aren't just abstract concepts, they're seismic shifts in perspective that transform how we see our place in existence. When you realize the iron in your blood was forged in a dying star's final explosion, or that the empty space around you might be a boiling quantum foam, the universe stops being a distant spectacle and becomes something deeply personal. What makes modern cosmology so exhilarating isn't just the scale of its discoveries, it's how they collapse the boundary between the cosmic and the intimate. Dark matter's invisible web might structure galaxies, but it also threads through your body right now. The quantum entanglement that baffles physicists could be the same phenomenon that someday powers unhackable communication networks. Even the mind-bending idea of a multiverse, once confined to philosophy, now emerges naturally from the math of inflation and string theory, suggesting our universe might be one bubble in an endless froth of realities. Yet for all our progress, the greatest revelation might be how much we still don't know. Dark energy's accelerating push could hint at undiscovered dimensions. The holographic principle suggests three-dimensional reality might be a projection from some distant two-dimensional surface, and lurking beneath it all is the haunting possibility that time itself isn't fundamental, but emerges from deeper, timeless laws we've yet to uncover. This isn't ignorance, it's an invitation. Every answered question peels back another layer, revealing fresh mysteries waiting to captivate the next generation of explorers. So when you step outside tonight and look up, remember, you're not just observing the cosmos, you're part of its unfolding story. Those twinkling lights overhead aren't just points in the sky, they're reminders that curiosity connects us across centuries, from Galileo's first telescope to the James Webb's deepest infrared gaze. The universe doesn't reveal its secrets easily, but that's what makes the hunt so thrilling. Whether you're a seasoned stargazer or someone who just paused to wonder, we're all in this grand investigation together. Drop your wildest cosmic questions below. Who knows which one might spark the next great leap into the